Let's talk about the electrical energy stored in a capacitor. Capacitors are storers of energy for either short-term or long-term. Long-term storage include rechargeable batteries in a hybrid car or a fully electric car, and somewhat shorter term would be your cell phone rechargeable battery. And most capacitors in use in commercial applications, including amplifiers and other electronic devices, have a very quick discharge of this energy. They store it for a little bit and then they immediately discharge it when it's needed. So in order to study how energy is created and stored, essentially when you have a capacitor which has not been charged or no voltage has been put there, it's got no energy in it. The reason you have any kind of energy is when you have a plus charge on this terminal or this plate and a minus charge on that plate, and they're marooned in that fashion. So there's a potential difference and electric field exists between those two charges, because electric field points from the plus charge to the minus charge, from a region of higher potential to a region of lower potential. So this electric field starts getting created, and that is the origin of the electrical energy in the capacitor. So to study this process more systematically, let's imagine charging it up. So I put a battery, and this would be similar to charging your cell phone when it's completely out of power. When the battery indicator is low, what you do is you attach the cell phone to a transformer that is sold along with the cell phone, and what that does is it takes the wall outlet voltage and converts it to a smaller voltage which is suitable for your cell phone, and then your cell phone gets charged. Let's examine this process. Now, the charge on a capacitor is related to the voltage on a capacitor by means of the equation C equals Q divided by V, or in other words, Q equals CV. So that graph is a straight line of slope C, where C is the capacitance. Let's draw this straight line on this graph. So at any moment, the slope is C. Now, let's imagine that you have charged up the capacitor to some voltage that is less than the total complete voltage. I'll call the complete voltage V0, and some intermediate stage. So this is where your cell phone is maybe 50% charged. All right. Let's imagine that I want to add a small amount of charge to the capacitor. So the phone is continuing to get charged. So I'm going to add this small amount, delta Q. Now for that small amount of charge, basically what's happening is you're transferring that amount of charge from the earth and putting it on this side. So you're taking delta Q from here and transferring it over there. As you keep doing that, this becomes more and more negative, and that becomes more and more positive. So the amount of work done is the charge transferred times the change in potential energy. Now you've taken it from ground, which is zero potential, and taken it up to the positive plate. So the final potential energy is V, and the initial potential energy is 0. And this work I'll call delta W. And to transfer that amount of charge delta Q, the amount of work done is that. Now what I'm going to do is I'm going to play the calculus game. In the limit that delta goes to 0, this is dW equals V dQ. But the voltage itself changes with time. However, the voltage change is given by this equation. So V equals Q over C can be used. So I get dW equals Q over C times dQ. Now it's in a very nice form. The left hand side only depends on W and the right hand side only depends on Q. So we can integrate the total work done by the battery, so I'll call it WB, is going to be the integral from initial to final of all these incremental works, and that's going to be from the initial charge 0 to the final charge, which I'll call Q0, because I've called the final voltage V0, let's say it's some target value here, and that's when your cell phone battery indicates that it's completely been charged, and you can now remove the cell phone from the outlet. So this can be integrated quite easily. It's 1 over c. Q dq is q squared over 2. So evaluating between the limits, I get that. Now the q naught is an awkward notation, so I'll just dispense with it. So the work done by the battery goes to increase the potential energy. The work done by the battery is an external agent, is minus the work done by the field. So the work done by the battery will go into increasing the potential energy completely. So WB equals delta UE, and the initial potential energy was 0, so this is just the electrical potential energy, and that's equal to 1/2 Q squared over C. That's one way of writing it. There are two other ways of writing it. One is by using Q equals CV. If I use Q equals CV here, I'm going to get 1/2 C squared V squared divided by C. One of the C's cancels out, and I get 1/2 CV squared. There's yet another way of writing this, and that favors Q and V. So for example, I can get rid of C. I can write C as Q divided by V. Let me do that. So that gives me Q divided by V times V squared, or 1/2 QV. Any of these three expressions is a legitimate expression for the electrical potential energy stored in a capacitor. So I'll write all of them in one line. 1/2 CV squared is the most commonly used by engineers, and then 1/2 Q squared over C you will use if you know the charge but not the voltage. And then if you know the charge and the voltage but not the capacitance, the ideal equation to use is 1/2 QV. I'm particularly fond of 1/2 QV because it is exactly the area under the curve. The area under the curve is 1/2 times base times height. So it tells you correctly that the amount of energy stored is just the area under that Q versus V graph. So any of these three expressions can be used. Now, I've been neglecting this story of the electric field. From the physics perspective, what's happening here is as more and more charge gets transferred, more and more of these delta Qs get transferred from the bottom plate to the top plate, there's going to be this electric field that's created. Now, in a real capacitor, the edge effects are going to become pretty important. And in a first course such as this, we'll simply pretend that the edge effects don't exist. We'll suddenly take refuge under Mr. Gauss again and say, oh, but Gauss said it's infinite. It's an infinite plate. So we'll play that game of deception. We're not going to worry about the edge effects. They're extremely important. The edge effects were first analyzed by James Clerk Maxwell, who used conformal complex geometry to study them about 200 years back. However, even though that's an important effect, we're just going to pretend that the electric field is just a straight thing. Okay? The electric field, because the electric field is the magnitude, that is, the change in the voltage over the change in distance. I'll call this y because this is the y direction. Okay? This is just going to be the change in the voltage is v minus 0, and the change in distance is just the distance between the plates of a capacitor. So we have a nice expression for the electric field. It's V over D. Or in other words, the voltage is the electric field times the distance. So that's a pretty significant result. I'm going to start boxing some of these things. That's definitely one of the highlights of this video. It proves that capacitors are used as energy storage devices, and that is no mean equation either. Okay, so now we have everything we need to talk about something more abstract. What is the energy stored not by the capacitor but by the electric field inside the capacitor? How can we find that out? The best way to find this out is to use one of these expressions. Let me use, it really doesn't matter which one, but I'll use 1/2 CV squared because that's the easiest to demonstrate. So let me take U sub E equals 1/2 CV squared and work with that. Well, for a parallel plate capacitor, the capacitance is given by epsilon naught A over D. And here I'm going to assume that we have got nothing stuffing the capacitor, no dielectrics, in other words. If dielectrics are introduced, the story gets modified, but we'll imagine there's no dielectric at this moment. And then voltage squared would be E squared D squared. One of the factors of D cancels out. Now I have 1/2 epsilon naught E squared times area of the plates times the distance between the plates. Well, that is just the volume of the capacitor, because area times distance is volume. Again, we're ignoring the fringe effects. Ignoring the fringe effects, A times D is just a cylindrical volume. If it's a cylindrical capacitor, plates are cylindrical, then that would be a cylindrical volume. The plate can be any shape. I've not told you what shape they are, but for any shape, it's just the volume of the capacitor. What I can now do is to divide both sides by volume. So I'll get what's called a specific energy density, or sometimes simply called the energy density of vacuum. Vacuum in this case because there's nothing filling the capacitor. And that's going to be U sub E divided by the volume of the capacitor, or A times D, and we get this expression 1/2 epsilon naught E squared. That's a very important expression. The energy density of vacuum has got the symbol little u. If that is uppercase U, that's lowercase u. Lowercase u equals 1/2 epsilon naught E squared. Now, if there is a dielectric in the capacitor, you will just replace epsilon naught by kappa times epsilon naught, and you'll be all fine. Okay, so that's the expression for the energy density inside the capacitor. Let's pause for a moment to figure out something very interesting about the energy density. It's got some familiar units. Remember, energy is measured in joules and volume is measured in meters cubed. Let's look at this unit more carefully. Joules per cubic meter. Well, joules is just work, so that's newtons times meters, because that's force times distance, divided by meter cubed. And if I cancel out a meter, I get newtons per meter squared. Force per unit area is also called the pressure, and pressure is measured in units of pascals. That's an interesting concept. The energy density in the capacitor creates a vacuum, and that's a vacuum pressure. In fact, there have been ideas for electrostatic vacuum cleaners based on this concept. You have two plates. Essentially, your vacuum cleaner is two plates, and you put a high voltage between them, and it'll suck all kinds of dust, because dust is a dielectric because of this suction pressure. In real life, this is how it's going to show up. If you have a capacitor that's got two plates and you try to bring a slab near it, okay, you physically bring the slab with your hand, that slab is going to get sucked in. That suction force is really caused by this energy density. Now, there's a physical way of understanding the suction force, and you can go back to your dipoles. All dielectrics are made of little dipoles, and these dipoles have plus and minuses. So the minus parts of the dipole and the plus parts of the dipole will get partly polarized. This is called the phenomenon of partial polarization. And because plus attracts minus and minus attracts plus, that attraction force can be rationalized as the force of suction. So you can understand the force of suction at the level of dipoles and polarization, but it can also be understood purely from the viewpoint of just unit analysis.